Hi everyone. Today I'm gonna talk about mesh loads and how to apply them to a grid of beams. In this small setup definition, we have a surface defined by 4 corner points. Those 4 corner points are our supports for Karamba, and we generate a grid using this surface, and these two directions of the grid are divided into the A and the B part. And those are inputted as IDs, so we can recognize them later on. So the next thing is we have a gravity load, a self-weight applied, and the mesh load we're going to talk about in a second. And then we have some cross sections. For the A beams we have I-shaped cross sections, and for the B direction we use a tubular cross section. This gets then analyzed, and a cross section optimization gets applied, and then just to view the model and the results. So back to the mesh load. We apply the mesh load using this surface, this meshed surface, and you can see we have a relatively coarse mesh and an uneven distributed load, even though the surface which this mesh is based on is the same size as our grid below. This is because Karamba calculates mesh loads using the mesh faces. The calculated mesh load gets applied to the closest element. If we turn up the U and V count for the mesh, we can see that the mesh load gets a little bit better distributed on the dedicated surface area. For performance reasons, I just leave it at 20 for now. And we apply a -1 force using this mesh. There you can decide if you want to see nodal loads or line loads. You can also just deactivate just one of which. Using this Karamba mesh load, it's a convenient way to project some loads onto a grid of beams or a lot of beams and add, like for floor slabs, weight. But you should keep in mind that the corresponding moments generated through the cross-section and the beam axis are not taken into account. With this mesh load component, and because we split it up into A and B cross-sections, we can then use the element ID to just generate mesh loads onto the B beams. And the same goes for the A direction. One thing you can do is, and another option you have, is orientation of the mesh. Right now, if I change these, nothing really happens. But if I take this reference surface and select a corner point and move this corner point for, let's say, down and a little bit to the side, you can see the mesh load changes because there are more mesh faces which are taken into account for the force at this portion of the grid. So the loads get bigger on this side. And also, if I now change it to local, you can see the tilting of the arrows. And this is because the force is now applied locally to the mesh for the mesh load, which means each face has a normal vector, and align into this normal vector, the load gets applied. This is useful if you want to like simulate wind pressure or suction. Global mesh, global projection projects the force into the z direction, and it's this way you can add additional weight to the mesh plane. And then you have global projection, which doesn't change visually, not that much right now, but this is used for the way snow behaves, or snow load can be analyzed with this option. Okay, this is mostly it for the MeshLoad component, and I guess that's it for today. Thanks for watching. Bye.